working on for quite some time now. And some of you will have seen a number of these slides, so apologies, but not everybody has. So I hope it'll still be interesting for those who have seen some of those slides. So this is an experiment where we've done VLBI on the crab between the MWA down here in Western Australia and the GMRT, so that I'll get to that at some later point. And just to remind you of what the crab looks like. So the crab supernova remnant, we've got the nebula around the crab, and the crab itself has got all these different components that we know and love. And besides these several components that are main and interpulse separated by about half a pulse phase, there's also all the giant pulse. And of course, the question here is always with the crab, can we measure the deflection between main pulse and interpulse? And can we actually also measure a deflection between, or sort of figure out whether the emission region of the giant pulse is different to the main pulses? And of course, we're still interested to figure out where the interstellar screen is. The interstellar screen, oh, by the way, so that's actually the pulse as the folded pulse profile as we see it at the MWA. So from Ramesh Garupasami's paper, they measure a pulse profile which looks a lot different to what we see at the MWA. Probably they measured it during an epoch of very low scattering, because otherwise I have no idea how to explain their profiles. But just going back to the scattering screens that we have, so the idea currently is that there is the one screen, which is the nebula, then there's the interstellar screen, and then there's us. And the current picture we have is that all of the temporal broadening, so all of the temporal smearing, is produced in the nebula, while whatever we see in angular broadening is from the interstellar screen. Now the interesting thing here is, if you take the temporal broadening of those 20 milliseconds, and you look at the interstellar screen and assume a cell size of that 10 AU, you pretty much quickly arrive that the interstellar screen would completely resolve out the nebula screen, and you would not see the nebula screen at the interstellar screen. And one question I ask myself is, where does this picture actually come from? So I went back to the very early papers because I had no idea why we actually think that the temporal broadening is all in the nebula while the rest is the interstellar screen. And so this is from Vandenberg et al. 1976. And this is the pulse profile at 111 megahertz at different baseline length. So the short baseline is the solid line, the long baseline is the dashed line, and the point here is that the profile looks the same. If the angular broadening was actually induced by the interstellar screen, you'd expect the pulsar to actually grow so you'd expect that at later phases, the scattering, the pulsar is bigger, and so on the longer baselines you resolve it out, so you have a narrower pulse profile. So that's the main evidence why we say that the temporal broadening is in the nebula and not on the interstellar screen. And then there is this other plot in the paper which I have trouble understanding, because they also come up with this as an explanation why all the temporal broadening is in the nebula. Namely, they plot the fringe amplitude as a function of harmonic number. And in the paper they actually say that the observations indicate, so hold on, no, the higher Fourier components should have a higher fringe visibility. And they're saying that at the higher harmonic numbers, the fringe visibility should actually be 1. And so this is old language, I suppose, and I still have no idea what the harmonic number in terms of visibilities is meant to be. I sort of believe it's meant like the UV distance, that the larger harmonic numbers are meant to be shorter baselines, so lower resolution, so we actually get the whole pulsar. That's sort of how I understand it, which is probably wrong, because only on the shorter baselines you'd recover the whole flux and then go back to a visibility amplitude of 1. That's my understanding, but that's probably wrong. Dan?
Is it possible that that harmonic number is simply harmonic of the pulse period?
That's what I thought initially. That's what I thought initially too. But why would you obtain a visibility of 1 at a higher harmonic number? I don't get that. What does the pulsar period have to do with the fringe amplitude?
Well,
I don't get that.
you're looking at shorter time scales, right?
So probably since then.
Yeah.
Is it a way of extracting the intrinsic, that is the repeating part of the emission, separating it from the scattered part, which is not repeating?
Probably.
It's
Yeah.
separated with the intrinsic and scattered profile, and that may be the argument. I mean, that
Maybe.
argument is made with the what's this new processing technique? I forget its name.
But
But on the other
yeah.
hand, there's in neither plot is there any effect as a function of harmonic number.
Exactly. So that's the main point, that there is no effect, that this is constant, constant across pulse phase, regardless of technicalities of how to understand that. Anyway, so we went ahead and did these observations between the MWA and the GMRT. We have about 30 megahertz of bandwidth, very different data formats. Martin has written all the nice decoding and stitching back together scripts, because the GMRT data comes in beautiful 5 files, and the data is split across the different files, different polarizations, 4 files, and a timestamp file, and everything is a bit funny. But Martin is smart enough to actually put this all together, so that's great. And on top of that, if you want to do VLBI, of course, you need to know your clocks, and you need to know your frequencies and your positions, which in particular with the clocks, we had no idea what the clock offset between GMRT and MWA is. And so here also, of course, the Crab giant pulses are beautiful because at the lower frequencies you have not so many as you have at the higher frequencies, and then you can just pick one giant pulse and unambiguously align the 2 time streams. So here, just again, we have the 6,500 kilometer baseline, projected about 5,000 kilometers. So around at our frequency, we have about 60 milliarc second resolution. Scatter broadening expected due to NE 2001 is about 100 milliseconds, so we're already expecting to actually resolve the scattering disk. And that was just for me to compare that I think it sort of adds up that when you put in the 20 milliseconds of scatter broadening and assume that the screen is at about halfway, you also have a size of the sketching disk of 128 milliarc seconds. So I think this is where this works. You could have sort of can reconcile it. Anyway, so here is a collection of a number of giant pulses that we did find fringes on. So signal to noise typically is around 10-ish. And I'll focus on one particular giant pulse here. The brightest one had a signal to noise of about 40 in the MWA and also at the GMRT. That's what the pulse looks like in a bit more detail. So this is where I got those 20 milliseconds from. That's the scatter broadening of that particular pulse. We have very slight hint of circular polarization. No linear, and the interesting thing here is, but that's a different topic, is that in the other pulses we actually don't see any polarization whatsoever, which is interesting in itself, because typically all those giant pulses are polarized to a high degree, which we don't see in any of those pulses. Sorry. Okay. So this is just to show the pulse, also the GMRT, they look different. Well, it's very similar, not different, and that's just manually offset just to make it clear. And the time offset we actually find between the time streams between GMRT and MWA is about 1.15 seconds. So trying to find this just in a normal correlator would have been quite a pain. Anyway, so those are the fringes. We do find fringes on that giant pulse and on the others across the entire band, because we typically correlate the channels individually. So this is just the delay you see here is just a residual delay, because we manually align the time stream. That's just the residual that we did not account for properly. You can take all of this out, of course. The nice thing you can do then is to have a look at how your residual offset scales with frequency. So here, so the black dots in the top panel, they're just when you use the same dispersion measure at both stations, and you actually see that the delay changes just because of a difference in the M. So we can measure the total electron content of the ionosphere, the difference in TAC between the site at MWA and GMRT. And we can also nicely measure the speed of light, really. So this all adds up.
So
this is ionospheric. So this extra DM offset is purely ionospheric. And so these are then the fringe amplitudes we find. So on the left plot, you see the whole about 300 milliseconds of data. So this is where the pulse comes in. This is pre-pulse, and this is just so crazy because we're removing the baselines and dividing small numbers by even smaller numbers. So this is a bit unstable. The main point here is that as the pulse comes in, we measure a fringe amplitude of about 1%, at least in this version. We actually have very different numbers and fringe amplitudes. We're still trying to figure that out. Main point here is that also as a function of pulse phase, we don't see any evolution. So the pulse does not seem to grow. It just comes in, it's there, and there is no evolution. So again, further evidence that there is that the temporal smearing or temporal broadening is all from the nebula. You can also look at the fringe amplitude as a function of frequency. So this is what I've done here. So I've averaged over a number of channels. In this case, each of these points is about 5 megahertz bandwidth. And in the previous plot, time resolution was about half a millisecond. Here I've averaged over 13 milliseconds just to boost the signal. And then you do see somewhat of a trend of an increase in fringe amplitude as a function of frequency. And what I've plotted here is as theoretical is using results, old calculations, Kolmogorov from 1987, where you assume Kolmogorov turbulence. And when you compute the visibility, it just depends on the phase structure function and the baseline length with a correction term for the pulse in the screen. You put in all the numbers, and then a by eye fit. So this is just putting in the numbers and seeing what works best with the numbers we have. The screen is at about 0.9 kiloparsec, so about halfway between us and the pulsar. So this is what we've done just with this one-dimensional baseline. Now the interesting thing, of course, is that once FAST is online, and they do have a receiver also around 150 megahertz, we should be able to do this again, but with 3 dishes, get phase closure, and get a bit of a better picture, also with a way more sensitive dish in there. And of course, for the short baselines, then with SK low coming online, we might be able to do a similar thing. So that's exciting. So that's all I have for that.
Thank you. Questions?
Well, Franz, that's a great job you've done at low frequencies of crab. So, did you have only one epoch of observations for this single baseline?
We have a follow-up observation, but that follow-up was actually more focusing on 0437, and that data is still in the can and awaits attention.
Yeah, it's because I'm asking because I was doing prep for multiple epochs, and we have estimated the distance to the screen can change a lot.
Right. Yeah. I mean, the distance to the screen is to be taken with extreme care, right? So this is really just a by eye what looks nice. So I wouldn't put too much weight on that. But yeah, we do have follow-up, but we don't have as much data. It's only about 15 minutes, where this is more than an hour.
Just to put it in perspective, if the screen is 100 milliarc seconds in size, it takes, I mean, this thing, the power motion is what, 1 milliarc second per year for crab?
I don't know. I have, don't know.
It'll take a century for you to move by a scattering. So for the scattering time to change in a decade is unthinkable physically, right? Because you're scattering over some large region, and you move by a small fraction of the size of this. To think that that's going to change in 10 years when you only move by 10.
The filaments in the crab nebula are moving.
So therefore, we go back to the original story: is that all the temporal broadening is caused by the nebula, and it's nothing to do with the angular broadening. In which case, this ratio really doesn't tell you anything about the distance to the screen. And then you have to ask the question: well, then how do we get a distance, right? So if comparing the time to the angle is not related, which I think is what Vandenberg said in 1976 already. That I think all of us see that there's no intrinsic change in visibility through the tail. So that's what Sidney realized, is that if it were a ring that's expanding with time, then over the couple of milliseconds the visibility would go from strong to much weaker because you've got a bigger So then you can ask, well, if you now ask, okay, so how am I going to get at this? I think the thing that would be interesting to compare also with the radio Astron data is that the rise time is sharp. So in the tail you've got no chance because the flux is swapping uniformly across the whole scattering disk. But because it's a very sharp rise, as you saw on all of these things.
Well, sharp, 2 milliseconds.
It's well, at least much sharper than it's 10 times sharper at least
Than the tail, yeah.
Then you have access, and what you expect to see is that you expect to see just the inside of your scattering disk initially filling up, and then so the initial edge should show a visibility change with time, and that's the place to zoom in. And it would be really curious to see whether with the last one you see any change in that rising edge. We are still debating whether we're seeing a signal there or not. So let's see. I think which would be interesting to compare.
Yeah, but that's a signal to noise issue, right? I mean, in the rising edge, getting the right signal to noise and getting something significant is quite tricky in those first, up to half millisecond regime.
You need that bigger telescope.
You do. But especially with the radio Astron, I suppose. Would you have the sensitivity to do that? I don't know.
So in these measurements of the crab, are there with the VLBI, are there any signs of echoes that have been recorded over the years? At many milliseconds late, they come in 4 or 5, 10 milliseconds after the main pulse.
Yeah.
We actually didn't check this in our data yet.
I see.
Not yet. You see, he's going to work on that. I think there's a data set that you just heard about that maybe should get priority. Because if they're there, that would be fantastic to look at, obviously. In some sense, if it's in the nebula, one wouldn't expect necessarily to see an offset, but at least the scintillation pattern should be different from the interstellar medium.
That would be very interesting. I mean, I guess I'd like to make another point is that the mathematics of temporal broadening favors scattering near the screen, whereas the mathematics of angular broadening favors scattering near the observer. So there's a bias in the way the line of sight.
Wait, the first thing you said, I'm not sure if you said it, I didn't hear it right anyway. The screen midway gives you the biggest
The temporal broadening.
No, the temporal broadening, I think it gives, from what we keep fixed, an angular deviation in the screen.
Let's see, I guess if you use the observed angular, then it's x1 minus x.
Yes,
X times 1 minus x.
But if you
But if you use the scattering, then it's different.
yeah, if it's
Scattering.
if you propose a certain angle of deflection,
Right,
scattering
yeah, then
angle,
it is different.
then that's much more powerful if it's happening in the nebula.
Yeah, that's right.
So a milliarc second of scattering in the nebula can have a bigger time delay than it would if it was near the Earth.
Yep.
So that's sort of a bias in the process.
Yep.
Okay, any other questions? Great, let's thank you. Okay, well now Michael will talk about scintillometry with VLBI at extreme angles. We haven't had extreme.
No. It's scintillometry with VLBI at extreme resolution.
Okay.
But it's
Sentence structure.
well, and in my defense, to any other audience in the world, the VLBI would be extreme angular resolution. It's just unimpressive to a scattering community that regular achieves higher resolution with all these amazing tricks. Techniques. Tools of the trade. Ah, yes. Okay, well, yeah, so I'd like to shift gears a little bit. The difference in what I'd like to share today over what we've been talking about so far is that I want to tell you about scintillometry and AGN, actually. And I think all of us have this idea that pulsars are point sources. They're kind of perfect scattering probes. But AGN actually have a lot of advantages because they quench the diffractive scintillation. And in some ways, we've already seen with the radio Astron data, the diffractive scintillation can be very complex to understand and to use for comparisons with theory. So I'll show you at least a few ways in which AGN might be able to provide some insights that are difficult to achieve with pulsars. So I'd like to focus on two experiments in particular that are pushing towards these extremely high angular resolutions directly. The first is the Event Horizon Telescope. So the EHT is this project to push VLBI to 1.3 millimeter wavelength. And so it's achieving its angular resolution by this push to the shortest wavelengths possible. When it's done, it'll have an angular resolution of about 20 microarc seconds. And the main goal is to image black holes with angular resolution comparable to their event horizons. So here's an example. This is a simulated image of Sagittarius star, our galactic center supermassive black hole. And this is a simulation by Avery Broderick. And the key features here are that you'll notice the image has this bright patch on one side. That's because it has an accretion disk around the black hole, and that's the side on which the disk is flowing towards you, and so it's Doppler boosted. It's faint on the opposite side. That's where it's Doppler deboosted. And you'll notice there's this bright ring of emission around the boundary that corresponds to the lensed photon ring of the black hole. So it has a diameter of about 5 Schwarzschild radii, and this diameter is almost independent of the spin of the black hole. It only changes by about plus or minus 4%. So it's a very generic and very robust feature that we expect in strong gravity, and that's one of the key goals of the EHT to probe. So you can see this is kind of the nominal resolution of the EHT once it's finished, and so we should be able to detect features like this. Now the second project is, of course, Radio Astron that we've already heard a lot about. Radio Astron is observing at longer wavelengths, but it buys back the resolution by going to space, so you get longer baselines. And so the best resolution of Radio Astron is about 10 microarc seconds. And a key goal here is to explore the highest brightness temperatures in AGN in the universe. And this is an interesting measurement because you can't get around going to longer baselines. They're needed. So this was one of the key science goals of Radio Astron. So the main question in my talk is basically, how are these goals of the EHT and Radio Astron affected by scattering? So it turns out there are two effects of scattering. One effect is very well known in the AGN community, and that's that scattering blurs out your images. So if you have some compact AGN and you observe at long wavelengths, you'll see that you can maybe resolve it. You see a large size, and that's just caused because of the scattering. So this is a deterministic effect. It's invertible, and it gets weaker as you go to higher frequencies. And one interesting thing about it is it doesn't affect some interferometric observables like phase. So closure phase, for instance, is unaffected by this type of scattering. So you can still learn things about your source even if you don't have a precise model for the scattering. You can infer things like anisotropy. Now, the peculiar thing is that there's a second effect of the scattering that does precisely the opposite. And this is caused by refractive modes in the scattering screen. And this introduces substructure in the image, just like in this picture behind the contrails of a jet. So in this case, it's this hot, turbulent air. And when you're peering through it, you're seeing all these fine-scale features. And the interstellar medium does actually the same thing. And the odd thing here is that it can introduce structure at scales that are smaller than those of the source. That is to say, you might have a long baseline that would have seen nothing. It would have completely resolved the source if there was no scattering. And yet, once you add the scattering, you have signal there. And so this has been the real complication in interpreting certain types of measurements. The other peculiar thing here is that it's stronger as you go to higher frequencies. So it really is sort of the opposite of the blurring. It's introducing substructure instead of blurring, and it's stronger when you go to higher frequencies, whereas the blurring is getting weaker. So I'll focus on this substructure. Here's a simulation of the substructure in the upper left here. What this is it's just a ring of emission that's completely constant, is the source. And then I'm scattering that and sliding the scattering material across the line of sight. So you can see how that image is evolving over time, all because of the scattering. And so from this, you can kind of imagine what the effects will be on observations. The first is that on your longest baselines, you're going to see this extra power from the small scale structure. So here's an example. These are observations of Sagittarius star at 1.3 centimeters. On short baselines, you basically see an anisotropic elliptical Gaussian. But when you go to long baselines, all of a sudden you hit this floor where all of this extra substructure is popping out. And so that looks like a noise floor. Those are high SNR detections. Those are not false fringes or something like that. The other thing that it's going to do is it's going to introduce these anisotropies in the image. So here's an example where we observed Sagittarius star at 3 millimeters. And we added the LMT in Mexico to the array, to the VLBA. And for the first time, we detected non-zero closure phases in Sagittarius star at a very, very small level. So this is exciting. It's telling us there's some sort of asymmetry in the source. And so people want to be able to say then, oh, this means that there's a jet or some sort of elongation or some interesting structure associated with the source. But the problem is that the level of closure phases we measured are actually consistent with what you would get if you just scattered a circular Gaussian blob. And so these are just two examples. You know, you can imagine, let's say you have one measurement out here, and you take that and you're trying to infer the size of a Gaussian source. You'd be enormously off in your inference. So these are two cases where if you don't account for scattering, in particular refractive scattering in your measurements, you can draw completely the wrong conclusions about your source.
Michael, what are the percentages in this dashed line?
Oh, so these are quantiles of the refractive. So this is a stochastic effect. And this is for just kind of the garden variety. If we had no data at all, this is the model we would have expected, basically. And so the median value of the amplitude we expect is here. But if you go back and look on different days, you'll see different levels of the substructure.
So that's at about 1% of the peak.
That's right, yeah. And so that will depend strongly on wavelength. At this wavelength, it'll go up as you go to higher frequencies. But then the source is also becoming larger relative to the scattering, and so that'll quench it. And so it actually remains at about that level, even all the way up to, you know, hundreds of gigahertz. Yeah?
When you're saying garden variety, is that a Kolmogorov assumption?
It is Kolmogorov assumption along with the inferred intrinsic size of Sagittarius star at these frequencies. Yeah. So I'll show you. I'll show you a preliminary image. This is. I don't know. There may have been other non-Gaussian images of Sagittarius star published, but I think this is the first one that's actually real. So this is at 8 gigahertz. This is Sagittarius star. It's an image. And if we were to make this image 10 years ago, we would have said, oh my gosh, look at all this amazing intrinsic structure. There's elongation. Maybe it's a jet. You know, we would be inferring all sorts of interesting physics here. It turns out this is perfectly consistent with just scattering a circular Gaussian blob. Well, the whole scattering picture, diffractive plus refractive, yeah.
So the elongation is the scattering, the blurring effect, right? Where is the refractive kernel?
Well, so this elongation is the anisotropic scattering. The refractive part of it is all of these stripes and splitting the image in different parts. And if we had a higher resolution array and better sensitivity as we push that, we'll see more and more substructure, all from scattering. What about radio Astron? So here's an example. This is just a simulated image. On left panel there, that's an unscattered source. And I'll show you parameters corresponding to a brightness temperature of 10 to the 13 Kelvin at the 3 key radio Astron wavelengths. So this is how the source would look like after scattering at those 3 wavelengths. Now, suppose that you have one measurement on a really long baseline. The question is, what does that one measurement of the correlated flux density tell you about the brightness temperature of the source? Now, this might seem kind of like a goofy toy model or something, but this is actually the case in radio Astron. You're on such long baselines that you basically have this one measurement to all the Earth stations. They're all equivalent. And all the ground-based stations are giving you information about, you know, larger scale structure in the image. There's a lot of structure in these AGN. And so you don't necessarily know how that long baseline measurement relates to any of the shorter baseline measurements. They could be probing totally different structures. So what can we infer from this? So it's kind of amazing, actually. Even without knowing the total flux density of the component, we can still estimate the brightness temperature. And here's how the game goes. So let's say that this is your measurement of flux density. And I'm going to, along the x-axis is the total core flux density of that source. So the red here is showing you what you would infer if what you're measuring is signal. There's no scattering. So if the total core flux density is the same as what you measure, then you're looking at a point source, and it has an infinite brightness temperature. Now, if the core flux density, you increase that a little bit, then you have to offset that and say, okay, my baseline must be partially resolving the source. And so then it turns out that the brightness temperature will initially fall, and then it'll go up. And you have this absolute minimum at a particular core flux density. So that's all without scattering. But now let's say, what if the thing that we're measuring is actually refractive noise? Now, in that case, you also have this asymptotic limit. There's some point at which what you measure is what you would have measured if it were a scattered point source. So that's when it asymptotes to infinity. But the interesting thing here is that as you go to larger and larger correlated flux densities, it plateaus to a constant value. And this is very stable. And so in this particular case, 3C273, the likely total flux density of the component is something like 5 to 10 Janskis. And so you can see that the refractive noise, in this case, this one measurement of refractive noise actually gives you a very stable estimate of the brightness temperature. And also, if you said, okay, I know the total core flux density, and if you interpreted what that was without scattering in the equation, you'd be off by a factor of 10. So again, this is a case where scattering is a critical ingredient in correctly interpreting the data, but also scattering helps us when we have sparse data. It provides more robust estimates of the brightness temperature than you would get if your uncertainty is anywhere along this curve. So it's kind of cute. We wanted to do more with this, and the problem is that these types of calculations in the simulations are very expensive. So the calculations, for instance, we can only calculate the most basic things, the jitter on a particular baseline or something. But we wanted to know, let's say, what's the covariance of the noise among different baselines? And how can we improve the scattering to be able to scatter realistic simulations? So to do this, we used this old framework developed by Blandford and Narayan for pulsars. And the idea is as follows. You have these two modes, diffractive and refractive, in the scattering screen. Diffractive modes are tiny. These are on scales of hundreds or thousands of kilometers. And their effect then it can be approximated by an ensemble average. We assume that you're not resolving these at all. And so that's what's producing the blurring of your image. So that's this cluster of diffractive modes that are affecting you. And then you have this cluster of refractive modes on enormously larger scales, which are leading to all this substructure that instruments like radio Astron are measuring. So it turns out that the entire scattering problem is mathematically equivalent in this limit of approximating the diffractive modes by their average, as taking the unscattered image and blurring it, and then taking that and allowing your refractive screen to act to steer and magnify bits of that. And so here's the observed image in this case, and you can see you get back all that substructure, which is entirely caused by the refractive modes. Now, the beautiful thing about this framework is that now we can do analytic estimates of many types of things, including the covariance or evolution over time. It speeds up the simulations by about a factor of 10 to the 4. And we can also do things like simulate extremely strong scattering, which just isn't possible if you're trying to simulate all the different modes on the scattering screen at once. And this also provides a natural scattering mitigation strategy for instruments like the EHT and radio Astron. So I just wanted to walk you through that real quick. So the idea of this mitigation strategy is that instead of just reconstructing an image from VLBI data, we're going to reconstruct an image and the scattering at the same time. Okay, so this is it's similar in spirit to something like interstellar holography, but it's enormously simpler. So the idea is basically that we're going to use that previous framework and we're going to say, we don't know all of the modes on the scattering screen. We barely have enough data to make an image. But we maybe have enough just to reconstruct a few of the refractive modes. Okay, so we're going to approximate the diffractive modes by their blurring, and we're just going to reconstruct a few of the refractive modes. So the thing on the sky that's going to produce the visibilities we measure is this combination of a blurred image and the scattering screen. And it's that combination, that's the thing that we're going to be comparing with our observations. Now, it still might seem hopeless. How could we possibly learn all of this information from one data set? But I think that comparisons with adaptive optics actually are reasons to be optimistic. So in adaptive optics, for instance, they have to reconstruct a new screen on timescales of milliseconds. Whereas for us, the corresponding timescale is the refractive timescale, so it's days or months. Another thing is, for adaptive optics, the scattering is achromatic, whereas, of course, in the interstellar medium, it's steeply chromatic, and so we can use multi-frequency observations to our benefit. In adaptive optics, they have to do the mitigation in real time, whereas here we can do all of it in post-processing. We record the full coherent wavefront. And in adaptive optics, of course, they have lasers and guide stars. We don't have that. Even the galactic center magnetar is many orders of magnitude too far from Sagittarius star to be used for this type of mitigation. But what we do have is a very stable and well-known power spectrum for the scattering. So we can use that to regularize the problem and do much better. So here's just an example at 3 millimeters. In this case, I'm just simulating an unscattered source that's a ring, just a geometric toy model. And here's how it would look like after one realization of the scattering. Now on the right here are 3 different image reconstruction strategies. So I'm just generating a fake observation where I sample this image using an existing VLBI array. So the first image is what you would get with maximum entropy, so a conventional image reconstruction strategy. And it does a pretty good job of reconstructing the scattered image. That's what it sees on the sky. Now, another approach that you can do that's pretty easy is that you say, well, I know that there's this blurring of my image. I'm going to remove that part of it. It's invertible. But the problem there is you're amplifying the substructure in doing that. And so you reproduce the image, the image you reconstruct would have too much compact structure in it. And then this is what you get with the new framework, and it does better at kind of balancing those two. Of course, it's also reconstructing the scattering screen at the same time. So here you can see the reconstructed screen versus the true screen. It doesn't get all the fine scale structure, but it basically gets the structure down to the resolution of the interferometer. And this one screen then would describe the scattering at all polarizations and actually at all frequencies. And also, if you had observations over a few days, you could even use the same screen and modeled in a frozen screen framework or something. So there are a lot of ways to combine this and maybe do better. Here's one more example. This is for the Event Horizon Telescope, so 1.3 millimeters. The unscattered image and after scattering. Again, maximum entropy does pretty well at reconstructing the scattered image. Deblurring the image does okay, but it's producing too much fine scale structure. And then the stochastic optics does a little better at balancing the two and getting back some of those sharp features like the shadow. So I think that there are a lot of, I think that this could be improved a lot, but already we're seeing that it should be applicable for EHT data. So one direction where I think we could do much better is in understanding and using time variability. So here's one example. On the left, this is our GRMHD simulation of an accretion flow onto a black hole. In this simulation, about 1 second would correspond to about 1.5 hours in real time. So we expect, over a single observation of Sagittarius star, to be seeing all sorts of interesting activity. The gravitational timescale is 20 seconds. The innermost orbital periods are minutes. So this is not a crazy expectation. And the thing that's remarkable is after scattering, when you watch the movie, it's pretty easy to tell where the intrinsic variability is occurring. However, if I freeze it and all you see is one frame, then it's pretty hard to tell what's the structure that's intrinsic versus what's the structure that's scattered. Right? It's difficult to know if I were trying to make inferences about turbulence in the image, what's what. So I think that there's really a lot of potential here to use that variability to be able to decouple these in a meaningful way. And just as one other example, let's say that you had some blob that's just going in a circular orbit around Sagittarius star. The scattering doesn't hide the periodicity of that blob. It actually enhances it. If you go to a very long baseline, you might have completely resolved it out before. The scattering gives you back that flux, and it'll be modulated with the period of the blob. So there are some ways, I think that there's potential for using the scattering to enhance time variability studies of Sagittarius star, but this is something that we're only beginning to look into. So just to summarize, scattering really poses some complex challenges for high-frequency VLBI. We have these two opposite effects. Diffractive effects blur images, refractive effects add substructure. And the key here is that it's a fundamental limitation on VLBI. You can't get around it by building a bigger instrument or going to wider bandwidths or anything like that. The only way to improve our understanding of it is by developing better techniques and better models for the scattering. And this is going to become increasingly important as we continue to push the higher angular resolution. Right? It's become critically important with the advent of these two recent arrays in ways that we didn't expect, and I think it will continue to surprise us. So just to summarize for the EHT, At 86 gigahertz, we just added ALMA to the array. This brand new, amazing array that's going to transform what we can do. But I expect that every single baseline to ALMA will be dominated by substructure. So this great array isn't any good unless we can understand the scattering and mitigate it. For the EHT at 230 gigahertz, substructure is important, and we have to understand how to disentangle it from intrinsic structure. And at 345 gigahertz, you can see a sample image here, the scattering seems to be pretty negligible. So if we can push to higher frequencies, then we may not have to go through all this pain. For radio Astron, we've seen that substructure can really affect inferences about high brightness temperatures, but it can also improve our ability to make those inferences when you only have a few measurements on a long baseline. And one thing I'll just advertise before closing is that all of the scattering code that we're using here is open source. It's available. Please get in touch if you think it might be interesting for a problem that you're working on. And yeah, we'd love to keep expanding it to new topics. So thanks for your attention.
Questions, comments? Yes, Jason.
So in your framework here, you do then reconstruct the phase screen that was mentioned yesterday, something you managed to do. So can you try this on some of the wonderful data sets that were shown yesterday? Or you were saying you can only expect to do a few largest modes or something. But in data that have these arcs or other things, could you then reconstruct higher order modes? Really not have a phase screen?
Yeah, so I think the ambitions on data like that are much greater, and these frameworks like interstellar holography and so forth are trying to reconstruct, all these stationary phase points effectively. It's because you have so much more information in the diffractive scintillation, all this frequency and time structure. Here, this framework, I think a similar framework could be developed for diffractive scintillation, but wouldn't be as powerful. This should be applicable to any radio Astron observations of AGN, anything that quenches the diffractive scintillation. But I don't know offhand any imaging experiment with radio Astron where this could be immediately tested. I'm sure there are some.
Yeah. Michael, I have a question about your splitting of things between diffractive and refractive scintillation, which is...
Not mine. Roger Blandford and Ramesh Narayan.
Yes.
Repurposed.
Yes.
Yeah.
Could you just go back to a slide that might, sort of have that decomposition?
Yes.
Yeah, that's great. So, since we have the person in the room, Barney Rickett, who brought us refractive scintillation, so I know that in many settings we can, strictly divide the world between diffractive and refractive, and just have those two things. But I'm wondering whether that's strictly true in this case. But to try to get to a question about it, so on that refractive phase screen that you're showing, it looks to me like you have a very large range of angular scales present in that. I mean, well, let me ask first as a question. Is that true?
Yeah, all angular scales, that are weighted by Kolmogorov power spectrum in this case.
Right.
Yeah.
So then there's no restriction along those lines. I mean, you haven't made any simplifying assumption there. It's just, I guess, the refractive size scales that are on the far right-hand side are much larger scales than the diffractive scale in the middle. That was part of your point.
These are all the same field of view. If to plot the diffractive scales, it would be a tiny speckle pattern. Yeah, you'd see.
So, okay, to try to clarify my question then, but the size scales on the phase screen, those are radically different size scales.
That's right. So the characteristic size here will be the refractive scale, or if it's an extended source, it'll be the angular size of your image. The characteristic size here will be the diffractive scale. So that's, commonly 1,000 kilometers or something. This is the thing that's producing these incredibly fine angular resolutions for inferences that use them. But maybe to put your mind at ease, when you do calculations in this framework, you reproduce all of the results, over the last 30 years for flux modulation and image wander and all of these to actually produce analytic estimates of these things, people have had to make approximations along the way. They turn out all, as far as I know, to be equivalent to this decomposition. One other interesting thing is that you're correct that this works best when your scales are widely separated, so when the scattering is very strong. But if you have an extended source, it allows you to push even beyond into the weak scattering regime. This was realized in the 70s or 80s also. So it's actually a very powerful and very robust approximation. It's, yeah.
In the transition region, I think the transition frequency is about 100 gigahertz.
For Sagittaire, it's a few terahertz, depending on how you define it. But
anyway, there you might have more focus, you know, the refraction and the diffraction kind of merge.
Right.
As regime, so you might have more focusing events.
It turns out, yeah. So it turns out this would still be okay for Sagittaire because the source is extended. Yeah.
But it'd be complicated for a point source.
Yeah.
So what are the prospects of going actually directly from the observed observed and refracted image to the unscattered image? Do you have to use actually the frequency dependence? I mean, you showed us simulations and you actually put in a particular model.
Yeah.
If you want to go back from what you observed to the unscattered image, you have the information of different frequency images, and the diffractive and refractive effects are frequency dependent. Is there any possibility to automate it perhaps in a way by having multi-frequency images and then learning something about the screen parameters to go directly to the unscattered image?
I think if you had very wide frequency coverage, there might be some way of doing that. For, again, Sagittaire quenches all the diffractive scintillation, so everything is refractive. Yeah, I don't know a simple way of doing that, of going directly from the images you recreate to a direct inference of the scattering.
Can I follow up on that? Because I'm convinced, I feel an incredible disconnect here. Because all these parabola features which are not frequency dependent, they don't behave at all like they're supposed to.
Yeah.
And yet you're using a model with a distraction. I mean, Bailey keeps arguing to me that it's on a size scale that you really don't expect anything. It's a way larger than the mean free path, way smaller than the mean free path particle. So how can you? So is something that we actually reproduce the parabolic arcs? Would that also reproduce what you scatter?
None of this nearby ISM.
Yeah, okay, so the idea here is trying to image pulsars to learn about the origin of the strongest interstellar scattering that's seen. So towards the galactic center, sources like Sagittaire, and then other high tau, so highly strongly scattered pulsars. So size scales here in this talk that are more like an arc second at 1 gigahertz rather than we've heard so far of a few milliarc seconds or whatever at hundreds of megahertz. Okay, and this mostly an observational project done with a lot of people, including a few in this room. I want to highlight Adam Deller and Jeff Bauer, who did all the hard work on the VLBA data analysis that I'll talk about. Okay, so it's really interesting, I think, now becoming a puzzle again about this intense interstellar scattering that's seen towards the galactic center and other regions as well, but specifically in the galactic center, where this is some compilation of scattering sizes. The plus symbols are maser sources where you can measure angular sizes. The cross is Sagittaire, the black hole at the galactic center itself, the radio source. And these open circles are at least claimed measurements for extragalactic background sources. And here's kind of a radio emission map just showing kind of the scale of the region. So this is supposed to extend over kind of 1 degree or half degree scales of some intense interstellar scattering. And
just to see, the size of the circle is the apparent size of this background.
So this cross, Sagittaire, is about 1 arc second at 1 gigahertz as a scale. The radii are supposed to, so there's a couple sources that are bigger, right? A couple extragalactic background sources that are bigger. Mm-hmm.
And the contour there?
Is some radio emission map, some continuum emission map at, I don't know exactly what frequency.
Different scale. I mean, this is a degree across an arc second.
Yes, these are not drawn to scale. They're not all overlapping with each other. Yeah, that's right. And same, even worse in the plots I'll show later of our results, right? The scattering sizes are always on a different scale than the galaxy coordinate sizes.
Yeah, and so I think very naturally it was assumed when first finding this that there's a lot of hot gas, a lot of ionized material and turbulent material, energetic material in the galactic center itself. And so it was assumed that all of this was arising on scales in local to the region. And this had immediate implications because for these angular sizes, for a local screen to the galactic center, this means, for instance, it would be very, very difficult to detect pulsars because the temporal broadening coming from this type of angular broadening would be enormous. So thousands of seconds, say, at 1 gigahertz, and wipe out all pulsed emission from this region. So, okay, and recently this story has changed a huge amount with the detection of the magnetar in the galactic center. And so this magnetar was detected in X-rays, not detected as a radio source. And so it would have been a very good bet then if you went 0.1 parsec from Sagittarius star, I should say, so well within this region, a few arc seconds away from Sagittarius star, so well within this region of all of these strongly scattered sources. And it would have been a very safe bet then, I think, to say that you should not detect pulsed radio emission from this object. And even if it was there, which is very rare for magnetars, you should expect it would be completely wiped out by this scattering effect. Instead, nice pulses were seen at normal radio frequencies with a temporal scattering time that was more like 1 second here at 1 gigahertz, so something like factors of hundreds or 1,000 below what was previously expected. And so then, you could say it'd be a little fine-tuned, but you could say, well, this is just a hole through this very intense local scattering screen. You got very lucky with this line of sight, which was randomly chosen, right, because it was detected as an X-ray source. But then Jeff Bauer et al. Went and measured the image of this source and found that it has an identical elongated Gaussian structure to Sagittarius star itself. So, and you can match this over many frequencies, showing that really whatever is scattering, causing the angular broadening of Sagittarius star, is clearly also scattering this magnetar source. So basically the strong scattering shown in that last plot is associated now with 1 second of tau, not with 1,000 seconds as previously thought. Okay, and then very similar to the studies of nearby pulsars that we heard about this morning and done in past work, you can immediately then in a thin screen model locate the scattering along the line of sight to the object. And so in Jeff's paper then, this distance from Sagittarius star to the scattering was given as 6 kiloparsec rather than a previous best estimate that was like 100 parsec or so, very local to the GC, right? Just because you did not have this magnetar, you could not look at this directly and just find out what the answer is. Okay, now I think there's revised estimates. It's somewhere something 4, 6, something like this, but definitely not in the galactic center itself, along the line of sight, and that's how you explain that this tau is so much lower. This immediately opens up a lot of questions because now it's much harder, I think, to explain why we don't see lots of pulsars towards the galactic center. We see lots of young stars. You should see a bunch of pulsars. That's an interesting open problem immediately kind of opened up by this. And the other interesting thing is that now we have a screen, a very strong screen, one of the strongest scattering regions that we see in the galaxy, that's a foreground object along the site right in front of a black hole in the center of the galaxy. So what happened there? So immediately ask, what is causing this scattering? Is this normal that it could be along the line of sight? And so for us, the thing to look at is what do we see for other pulsars? So we can try to repeat this experiment for other very strongly scattered pulsars. Unfortunately, there aren't any very close to Sagittarius star, as we said. So the closest ones are kind of 10 parsec away, shown here in the tau, the temporal broadening versus DM. So these guys are all in the galactic center. Here's the magnetar. Here are the few others that were known from these past discovery papers on kind of scales of 20 parsec or so, still within our plot of this strong scattering region, but outside of kind of where the young stars are seen in the galactic center, for instance. Okay, and then we also did a few non-galactic center pulsars, but still in the inner galaxy as well. And so here's what they look like. Yeah, here's a zoom in of the plot from before with some of these source sizes. Again, definitely not to scale. I mean, here are the pulsars. So here's the magnetar, and here are these other three that we looked at. And these are, the challenge here is these are very faint, right? Far away high DM pulsars, highly scattered pulsars are very, very faint. So we had to, for these ones, we had to use VLA plus VLBA observations. And for the other ones here, we just use VLBA only. But these are very difficult to detect. So we can't do beautiful scintillation arc studies. We try to just measure a size. Measure a size of an object, locate a screen, kind of a very simple experiment. And in the best case, it turns out something like this is one of the galactic center ones. This is its image. And here's the visibilities, and you can fit a size. This is a model of the complex visibilities. So some position offset and some size is what you measure here then, with a size at the observing frequencies we used, which were between 5 and 9 gigahertz. Here, this one was at 6 gigahertz of 11 milliarcseconds inferred from this. Okay, so now we can look at that for all the sources that we looked at. So this is two kinds of plots that I'll show, right? Because we now have kind of 3D information. So this is just the positions of the objects in galactic coordinates. Here's the galactic center region. Here are the other three outside the galactic center. And now the two circles are the outer and inner plus or minus 1 sigma sizes. Again, not to scale on this plot, right? But so again, for scale, here's the magnetar in gray at kind of this 1 arcsecond at 1 gigahertz scale. Okay, and the immediate thing to notice is that these other galactic center pulsars are all smaller in angular size than the magnetar, which means that in the thin screen picture, the scattering arises closer to the galactic center than for the magnetar. And in particular, this one here is really only an upper limit, as far as we can tell, and it's very high tau. And so, 2 seconds or so, or 1.5 seconds, and at 1 gigahertz. And so this one seems like it's immediately then evidence for scattering that's close to the galactic center itself. Not 1,000 second of tau, right? Because we see it as a pulsar. But
Chase,
yeah.
I asked this question maybe the last time I heard you.
Yeah.
Are you assuming that the objects are all at the same distance from us?
Yeah, so these guys we put all at the galactic center for lack of a better thing to do.
So you could move one of the pulsars, it's the same screen, but you could move it closer to us, and you could then get
to match a location. Yeah, that's right. But it would have to be at 4 kiloparsecs instead of 8 to match the same screen location. That's true. Yeah, but that is true. Yeah, so we assume that they're all at the galactic center itself. In projection, they're quite close.
I think it's
No, but that's true.
But there is a small loophole.
Yes, that's true. Yeah, for these guys, that's true. Yep, and then so the outside the galactic center, I think it's interesting. This one is actually comparable then in angular size to Sagittarius star, slightly smaller, but also with a smaller tau. And yeah, you can see the other ones here. And now, right, because we have these are pulsars, so we have temporal broadening measurements from the literature. So now we can combine this and do the 3D version of the plot. So now shown as the galactic longitude, but now with the distance along the line of sight. So the best estimates for the locations of the pulsars are the stars. So here, these ones again are all put at the galactic center, and these other ones are. So I think this one is the H1 absorption measurement that I mentioned earlier, and these two are DM, NE 2001 DM distances to the objects. Okay, and so now you can see again that the small sizes of the galactic center ones mean that they're all kind of closer to the galactic center itself, quite close actually, in scattering location, thin screen location, whereas these ones all seem to be sort of at this same 2-3 kiloparsec type location, so some foreground location similar to what's seen for the magnetar.
So these circles are the location of the screen, and the stars are the location of the pulsar.
I like this plot, but maybe it's not intelligible for anyone except for me. But I like it. I think it's great. So the error bars are the location that's inferred, so matching to the y-axis, the error bars. And then these circles are the same as before. So this is just the angular size plus or minus 1 sigma with some arbitrary scaling. So it's not matching to an axis, just showing you can read off the relative size relative to the magnetar, say, or Sagittarius star.
So the way I read this rightmost point at the latitude of 0 is that corresponding to 1745 minus 2900, there's this pink circle with this pink error bar. And then the other 3 galactic center ones all are explained by 3 screens that are near the galactic center. That's the way I read that one.
That's right. This scattering all occurs locally, and you can tell that because all the sizes are small compared to this one, while the tau values are pretty comparable. Yeah, that's right. Small sizes mean the scattering is quite close, actually, to the galactic center. That's right. Yep. So just we can just zoom in on that quickly, just showing this again. So I think it's important to keep in mind. So to me, the immediate takeaway from this to me is that on that first plot, you have a range of angular sizes over the galactic center that's all called the scattering region of the galactic center, in the literature. And now I would say we know that's not all one scattering region, right? There's not one common physical origin to explain all of those measured angular sizes, right? Before it, we knew before that the sizes can vary, but that could just be a patchiness in the medium itself. Now you know it's not. There's distinct physical origins over that scale, right? There's multiple components to explain the scattering on 0.5 degree scales in the galactic center, right? Or on 1 degree scales. And so you know immediately, for instance, that whatever physical object it is that produces this Sagittarius star magnetar scattering, it's between kind of 0.1 and 10 parsec in size, in physical size, whatever it is, right? Not the best constraint, but now we have a constraint. So it doesn't extend over this 100 parsecs of the galactic center, for instance. Okay. So to try to explain this, so the minimal model, if you really want to try to explain this, I think really it's that there's many distinct screens. But if you want to, you can make a minimal model for all of this, which is just 2 components. So you can say that we have one screen, which is here at the location of the screen that's in front of the magnetar and the black hole. And then we have another screen, which is local to the galactic center itself. Right? And so this one is needed to explain this one pulsar where it's really small in angular size. This one is needed to explain Sagittarius star and the magnetar. And now we can say that the other ones are combinations, right, of these two, where some fraction of the temporal broadening for this one comes from this, basically, while its angular broadening is set by this one. And so this then, from this model, then you can basically put limits on the strength of these 2 components as a function of the locations of these other pulsars.
So the other ones actually have, you're saying, more scattering time, and therefore the galactic center pulsar has to not be behind their screen. There's going to be a hole in those guys' screen to hide the galactic center magnetar, and vice versa. There's going to be that cloud that covers.
I mean, to me, it just means these screens are not that big in size, right? It's not a hole so much as it's just whatever the physical object is. It's just less than 10 parsec in size, so it can't cover the. Yeah, I mean, you could call it a hole, but I think it's just you've seen past the edge of whatever it is that's scattering the magnetar. But that's right. If you can't attribute the temporal broadening of the magnetar to this other screen, because these 2 objects have the same temporal broadening, there's just no way to do that, right? You'd have to move it even closer. It's already 2 or 4 kiloparsec away. You just can't do it. Yeah, put it at the Earth, basically. That's right. Okay, so this is, again, my interpretation from this, again, is just that whatever screen it is that's in front of Sagittarius star and the magnetar is just not there anymore out here. That would be my interpretation. You could say it's there and it just gets weak. We can't say the difference, but to me, this just means that this screen is smaller than 0.2 degrees in size and it doesn't cover these objects.
So what do you mean by relative screen? How are you measuring screen strength?
Yeah, so this is a fractional amount contribution to tau for each pulsar. Okay. Yeah, you could choose slightly different, but it's the takeaway, I think, is kind of the same. Yeah, it's a very simple, just assigning tau to this, and both of them to this, and calculating the fractions. Yeah.
But then I don't get it. The local screen is contributing most of tau to Sagittarius A star, the point at.
No, it's not contributing to the magnetar tau, right? So the magnetar pretty much has to be this, all from this one foreground screen, because otherwise it would have to be even closer to Earth, right, to explain its angular size.
So your GC block there is, where's the magnetar relative?
Yeah, sorry. Yeah, that's true. That's true. Yeah, you would. That's right. You would have to put some kind of. That's right. Yeah, that's true. Because it has to be a pretty giant object. I mean, so I'll say it in a second, but I mean, I think it's H2 regions.
Okay.
We have some constraint. I mean, it's hard already maybe to put a giant H2 region 2 kiloparsec away, but if you try to attribute all the tau from the magnetar to this, I think you have to put it like. It's not possible, basically, because their taus are like the same, right, for this. But yeah, I think it becomes even worse. All the problems you might have with this 2 kiloparsec result become even worse if you try to do that.
So why is it 2 kiloparsecs now when it used to be more like 4?
No, so in Jeff's it's 2.
Yeah.
Now I'd say Olaf and Wei Li would probably say maybe it's more like 4.
Yeah.
I don't, for my purposes, it doesn't really matter. It's a foreground, right? It's not 100 parsec.
I mean,
That's all that matters.
The
No, I mean, you would like to know that. That's right. Yeah, at that level, then.
There are regions where you'd expect
That's right.
to have we know there.
Yeah, I don't think we can rule out which H2 region, for instance, or which spiral arm. Yeah, I don't think we can say for sure. Okay, so I want to say for the other 3 sources, the interesting thing that we found is that all 3 of them lie next to H2 regions in 2D that are known, sharpless, well-known H2 regions that have measured distances. And in 3D, the locations of the scattering that we find all coincide with those H2 regions, so in 3D. So this is shown here as the blue squares. Again, this is our galactic coordinates. This is our along the line of sight and galactic longitude. And the circled things are the black are the H2 regions, and the blue are the scattering locations that we find. One of them is also with this supernova remnant here, but in 3D, the locations match quite well. So, again, previously we would have known in 2D, but now we actually get the distance matches as well. So to me, this is clear evidence that this very high tau pulsar scattering is associated with H2 regions or, other objects, right? You could then associate it with the stars in the center of them or the, giant molecular clouds around them, but with these regions in the galaxy.
What's the NE in those regions?
Yeah, so let's get to that. So you can then try to estimate what NE do you need. So we did this from the point of view of the strength of the scattering that we see. So you can just take, this is a very simple model of turbulent interstellar scattering, say that the fluctuations are just complete, are maximal, delta n is equal to n. Just for simplicity, if you change this again, it'll make the problem I'm about to talk about worse. So this is sort of, anyways. And then given the known size of the H2 region, if you say it's the whole thing that's scattering the pulsar, and the measured size, and we know its location, you can just estimate the density, its contribution to the dispersion measure of the pulsar, and other properties like the ionizing photon rate of the H2 region, right, to set the Strömgren sphere of the H2 region. Okay, so for this one, and it's given by this formula here in this paper by a master's student who is at MPE. And so now you can take an example of this one that, this H2 region here, here's roughly the location of the pulsar, this one pulsar. This is the most strongly scattered one. This is the one where the image was almost as big as Sagittarius star. And so now from this, you can infer a density that's about 200 per cubic centimeter. And this actually agrees really well with previous estimates from line ratios of what the density in the H2 region should be. So if you believe this, then that it's going through this, it's kind of at the edge, so maybe not quite through all of it. But if you estimate what the contribution is then to explain the scattering, what you expect for the DM, it's something like 1/4 to 100% of the observed DM towards this pulsar. Okay, and this is what I mentioned earlier, that this would strongly affect distances to these objects, right? That if you don't account for this as a, the different electron models have clumps along the line of sight, but this is a pretty dominant, about 10 times stronger or something than you would otherwise say for clumps. Okay, sorry, just very briefly wanted to say we then decided to do follow-up of more sources, and unfortunately detected very few of them. So the problem here is we're really limited by how faint the pulsars are, but you can at least add a few more sources to the plot now. And really, for the ones not in the galactic center, it's kind of striking that these high tau pulsars all seem to have scattering screen locations that are like 2 kiloparsec away from Earth.
So that's all low latitudes?
Yeah, that's right. These are all, they're pulsars, so they're all in the galactic plane, or high DM pulsars, so they're all in the galactic plane, and plus or less than 1 degree away from the galactic plane.
That sort of suggests maybe not the same location, right?
I have no idea. I mean, these ones also have to be explained, right? So it's not like there's not one steady screen, right? That's
again, there's more than one spiral.
Fair enough.
That's right. Yeah.
And a lot of H2 regions.
Yeah. Okay. So sorry, just the gallery that some of these are right on top of. So here, the white ones are the ones where we know the distances. So in these new ones, we can't say that they are associated because we don't know the distances to the H2 regions. But at least in the case of this one, I would say we now know the distance to this H2 region, I would claim, because it must line up with the scattering size that we measure. And then there's this one that was a very tiny image and weakly scattered pulsar, and but by our standards, and there's absolutely nothing here, so I don't know what's going on here. So there is one that's not associated with an H2 region. Okay. So just to summarize, you can use this technique of imaging pulsars, right? As we've heard, to make 3D maps of scattering locations. At least in this limit of the highest tau, the most strongly scattered pulsars, they always seem to line up with these H2 regions. We've also shown that there's some kind of local component to the scattering of objects in the galactic center, so associated with the galactic center itself. And it seems like if this model is admittedly naive, but it seems like a lot of the total dispersion measure towards these pulsars could really come from just the screen rather than, say, integrating through the galaxy. And my questions of how this all fits in is, so the main thing that we've talked about is, again, at the beginning, that we have this foreground screen that's right in front of the black hole at the galactic center and not associated with the hot gas that's right next to it. And so that implies that these types of screens must be really common. But we haven't really addressed that, right? So we look at the other galactic center ones, all the angular sizes are smaller. We look at ones elsewhere in high tau pulsars, the angular sizes can be big, but they're still smaller than Sagittarius stars. So it seems like these things must be really common. It'd be great to use some of these, very high resolution, say VLA data sets of the inner galaxy. It seems like you should be able to redo some of these background source experiments. I don't know, comparing the galactic center and somewhere nearby or something to figure out where are these other ones. And then I don't know how to, I think this was brought up at the end of the question session for Michael's talk, but I don't know how to reconcile this stuff with the 1D filaments and lenses and so on, because what we see are these very smooth Gaussian type things. The Sagittarius star itself is the best example of this. And then again, we also see that these are really seem to be associated with H2 regions at kind of kiloparsecs away. And I learned yesterday that some of these other smaller dispersion measure type scattering comes from these hot stars. So again, I don't know. I'd be interested in any ideas for reconciling all of this, or maybe it's just completely distinct, right? That local nearby bright pulsars just have a completely different origin of their scattering, right? Because you don't look through an H2 region. Okay, thank you.
Okay, questions?
I just wondered if your images are round, because it can fit a nice size to them.
Yeah.
Can you tell? Or is
I wish we could tell.
Yeah,
it feels like, so if you just look at in the images, if you just fit it in the images themselves, they're all asymmetric.
Right.
They would all give you 2 to 1, 3 to 1, which is not that surprising from Sagittarius star's image itself. But in the way that we do the fitting, we don't have high enough signal to noise, so it would say that that's not significant. So I suspect that they are, but if we just use 1D because that's all we can safely say, yeah.
There was another question, I thought.
Just asking the same question as Martin. So since you take, I guess, an angled average of the size at the end of the day,
Yeah.
Now just to get distances, though, the angle, so the scattering time is completely, if your lens is elliptical, the scattering time is completely swamped by the long axis. Okay, so that's the only thing that enters the scattering time. When you're adding quadrature, but if it's like 3 to 1, it's only 10% from the minor axis. So the time is all from the long axis, but we're going to take the geometric mean, which is actually half the long axis now because the other one is shorter. That means you're underestimating your distance by a factor of 2, isn't it, for all of them, systematically?
I guess maybe, but I don't. Actually, to me, that's not such a big concern. I don't know.
The broadening function it's much more concentrated towards the origin when you have a 1D thing.
Yeah, you could look at the tau and use the other anisotropic one, right? Where you have 2 directions.
Well, but the 2 directions add in exponential in quadrature, meaning the short one just doesn't do anything at all. And it's just a long one that, they add 2 Gaussians in quadrature. You only see the long axis. If you add them in an angle average, you get a different weight.
No, the scattering function would be different.
Yeah, it goes like e to the minus t over t.
Yeah.
Something like that. Or root.
Yeah.
Yeah, so it's not the usual kind of just.
That pushes it out.
I mean, of course, you could in your scattering function look for anisotropy in your scattering, as I think what René and Jim are saying. But those differ very, very subtly. So yes, sure, from the minus time and the decay rates, you can try to infer it. It turns out this is fairly insensitive to fairly extreme changes in axis ratios, which is what Aris has been, Aris and Marisa have been trying to do that. So that I think is challenging, and I think the data is probably consistent with quite a broad range of axis ratios, but of course I think that's.
Yeah, I think that this would be better studied for the tau than we can study it here. But if it was strongly not e to the minus t over tau, they would know from the pulse broadening measurements, right?
No, I think in both cases, both isotropic is exponential. Just the right time is a little bit different.
Okay.
It's a subtle thing to look for.
Well, maybe we should worry about it. The scale of all the other things to worry about, I think it would be maybe similar. I mean, if you want to pinpoint the locations, there are a lot more things, right? It's a single thin screen model. We don't have any way, we don't prove that for any of these objects. We know it pretty well from the wavelength dependence for the galactic center, but we haven't shown it for any of these other ones. So there's a lot, there are a lot of other things that could affect the distances at kind of order unity level. Yeah.
It might seem more if you just fit a total one-dimensional thing, at least it gives you a constraint, right? Because that has equal number of degrees. That gives that one more degree of freedom. You may just be able to tease that out of the data if you have a signal to noise view at least.
Yeah, I haven't tried it, but every time I've tried something other than a circular Gaussian, I've been very disappointed with the ability to constrain anything. I guess I would just put it that way. Yeah. Yeah.
Why couldn't you go to lower frequency? Wouldn't they get wider?
Yeah, so there's a trade-off, right? So if you go to lower frequencies, the pulsars get brighter, the sizes get bigger, and the calibrators get much worse. So these are all phase-referenced observations. The calibrators themselves then get fainter, effectively, because they're heavily scatter-broadened. They're usually just as or more scatter-broadened than the sources themselves, because they're pretty nearby and they're extragalactic sources. So it's kind of, we tried to do this balancing act of, that's right.
But
so
if you know enough that you see the scattering, you can do almost a type of trick where you just watch the ring and calibrate the ring to itself, then you don't need an external calibrator.
So I was surprised. So in the follow-up observations, we tried going to lower frequency to 4.5 gigahertz because they were supposed to be weaker scattered. And then I thought it would get better, and we could just probably self-calibrate or something, and it would be okay to get a reasonable size at the end. At least we detect something. And instead, we didn't detect anything in more than half of them. So I'm not sure. No, at 4.5. Then the VLBA is not matched. You have to match, at least a little bit the size of the beam to the size of the. You don't. So that's what pushes the frequencies to these. Otherwise, yeah, of course, we'd rather go to lower and have brighter sources. Yeah.
So we have just a few more minutes before lunch, and I guess this is the discussion session. Did you want to?
No, I just said it was very nice.
Yeah. Thanks.